In 1994, a mathematician named Peter Shor wrote an algorithm that could theoretically break every encrypted message on the internet, not in centuries, but in hours. The problem? The computer powerful enough to run it didn't exist yet. 3 decades later, the world's biggest governments and companies are in a race to build it. This is quantum computing. So, what exactly is this machine everyone is racing to build? Let's clear up the biggest misconception first. Quantum computing is not just a faster classical computer. It's a fundamentally different way of processing information, one that exploits the strange rules of quantum mechanics that govern reality at the atomic scale. Here's the formal definition. A quantum computer is a physical device that processes information by coherently manipulating quantum mechanical systems, exploiting 3 core principles: superposition, entanglement, and interference. Classical computation is really just a special case of physical computation. Quantum computing is what you get when you take the underlying physics seriously, all the way down to the microscopic level. But why do we even need this new kind of machine in the first place? The answer starts with a trend that shaped the entire computing industry for 50 years. For decades, Moore's law held true. The number of transistors on a chip roughly doubled every 2 years, and classical computers kept getting faster, smaller, and cheaper. But look at what happens in recent years. That curve starts to flatten. Why? Transistors are approaching near atomic sizes. We're running into excessive heat generation, rising power consumption, and skyrocketing manufacturing costs. As a result, classical computers are struggling to keep up with some of today's hardest problems: large-scale cryptography, complex optimization, and accurately simulating molecules and materials. That's the gap quantum computing steps in to fill. To understand exactly how it fills that gap, we first need to get precise about what computation even is. Think of it like a recipe. Raw ingredients go in, a finished product comes out. More formally, computation is a 3-part pipeline: an input, run through an algorithm, producing an output. The input is a string of symbols encoding a problem. The algorithm is a finite sequence of operations, and the output is the resulting encoded string. Depending on how the algorithm behaves, computation falls into 2 categories: deterministic, where the same input always gives the same output, like 2 + 2 = 4, or probabilistic, where the same input can produce a different output, the way a coin flip does. And crucially, an algorithm is abstract. It's independent of the hardware. The same sorting algorithm can run on a silicon chip, a mechanical computer, or a quantum device. What changes with hardware isn't correctness, it's efficiency. That distinction between the abstract algorithm and the physical hardware running, it turns out to matter more than it first seems, because information itself is never truly abstract. In 1961, physicist Rolf Landauer articulated something foundational. Information is not an abstract entity. It is always tied to a physical representation. The implication is huge. The laws of physics determine the limits of computation. Every piece of information needs a physical carrier. A classical bit that's 0 might be an electronic voltage near 0 volts. A classical bit that's 1 might be a voltage near 5 volts. But a qubit? It's encoded as a superposition of quantum energy eigenstates, something classical bits simply cannot represent. This is the bridge between abstract information and physical reality, and it's exactly what makes computation subject to the laws of physics, both classical and quantum. Let's stay with that classical bit for a moment, because its simplicity is exactly what defines its limits. Every piece of information in a classical computer boils down to a bit, a variable that's either 0 or 1. That's it, just 2 states. And yet from those 2 states, your laptop runs an operating system, streams music, and connects you to the entire planet. Now here's where it gets interesting. For n bits, the total state space is 2 to the power of n. At just 10 bits, that's already 1,024 possible states. But here's the catch. At any given moment, a classical computer occupies exactly one of those states. It checks one configuration at a time. For most problems, that's totally fine. But for certain classes of problems, it creates a fundamental bottleneck, and that's exactly where quantum computing enters the picture. So which problems actually run into that bottleneck? To answer that, we need to talk about how difficulty itself is measured. Here's a puzzle. You can check whether a completed Sudoku is valid in seconds. But solving a blank Sudoku from scratch? That can take far, far longer. Why is checking easy but solving hard? This is the heart of computational complexity, the study of how problem difficulty scales as problems grow. Computer scientists sort problems into complexity classes. P is the class of problems efficiently solvable on a classical computer, like sorting a list. NP is the class of problems that are efficiently verifiable, like checking a Sudoku solution. And QP is the class of problems efficiently solvable on a quantum computer, like factoring huge numbers. Now, a common misconception: quantum computers do not solve everything instantly. NP-complete problems, the hardest problems in NP, like the traveling salesperson problem, are believed to be hard even for quantum computers. In other words, NP is likely not a subset of BQP. Quantum computers are faster for specific tasks, like factoring and simulation, but they still have real limits. Given those limits, it's worth asking what it actually is about quantum systems that gives them any advantage at all. In 1982, physicist Richard Feynman put it bluntly: "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." Here's why that matters. Simulating a quantum system of n particles on a classical computer requires resources that grow exponentially with n because the wave function lives in a 2 to the n-dimensional Hilbert space. A quantum computer, by contrast, naturally represents and evolves states like this. This gives us two sides of the same coin. On one hand, physics limits classical computation. Thermodynamics imposes energy costs on irreversible operations, relativity bounds clock speeds, and materials impose noise floors. On the other hand, quantum physics enables entirely new computation. Superposition lets amplitudes evolve simultaneously over all inputs, entanglement creates correlations no classical system can replicate, and interference lets us amplify the right answers while canceling out the wrong ones. So let's bring it all together. What computation actually is: input, algorithm, output. Why information is physical, thanks to Landauer's principle, and why quantum mechanics demands an entirely new kind of machine. Coming up next, just how hard are the problems that actually matter? Not all difficulty is created equal, and understanding the structure of computational complexity is what gives quantum computing its real meaning. That's where we're headed next.